Okay, guys, this is my barn. It's not the classroom. Yeah, this is the best I can do right now in the COVID era. This is actually a whiteboard I have up at my barn. It's been here. I got it from Mitchell years ago, and acetone does amazing things for cleaning a whiteboard. Don't breathe it. It takes the place of oxygen. It kills brain cells. So. What we're going to do is I'm going to finish up today, right now in this video. I'm going to do the infinite plane using Gauss's law, then talk about the curl of E, and then in the next video, this is effectively Wednesday's video. I'll put it on Canvas how I want you to do for the notes and stuff. I'm pretty much going to be out on Friday because I got to get a COVID test again at 9:30 on Friday. And so I won't be able to be back till Monday. So hopefully I'm going to put up enough videos that will count as Wednesday's lecture and Friday's lecture. And the video is either going to be done today or tomorrow morning, tomorrow afternoon. So I'll get those videos up. And once those videos get up, take notes from them. I'll probably have you turn in notes from both sets. That way I can give you a good grade, and that way I know you've watched them as well. So I'm sorry. I'll probably, once I fill up a board, because I got to use acetone to clean the board. So I'll turn the video off and we'll start up the video again. I'll either put them together or I'll just make them separate, depending on what the time allows. And the upload speeds I have at my house, which are kind of slow since I'm in the country. All right, so let's get going. Let's look at example 2.5. This we're going to do Gauss's law for an infinite plane. Infinite plane. I do have some marks in the board, but that's all right. That's the reason I got it. I think I got a surplus at Mitchell for like $5 because it had some scratches in it. Infinite plane with a uniform surface charge of sigma, I think. Yep. We want to know what is the electric field of that plane. Now, if you think of an infinite plane, you're like, why the heck would we do infinite planes? Well, you know, if you're in a desert, you know, on a horse with no name, some of you got that reference. You're going to look around. It's going to be flat, especially if you're not in the mountainous part of the desert. It's going to be flat this way. It's going to be flat that way. Go to Nebraska or parts of Kansas. The Earth is an infinite plane, you would think, because as far as you look that way, it's flat. That way, that way, that way, it's all flat, infinite plane. So when you think of the infinite plane, of course, there's not one, but we can approximate it, you know, if you're really, really small on a sheet of paper, because if you were the size of, you know, a grain of sand, a sheet of paper, looks, and you were on it, you could say, hi, I'm a grain of sand, I'm looking around. It looks like an infinite plane, probably, if you're looking at all the paper around you. So that's how we can think of it like this. And so this, while it may seem a mathematical exercise, is directly relative to real situations because, yeah, it's not infinite, but it's darn so close enough, we can just call the electric field this for a sheet of charge. And that's what this is, a sheet of charge. Okay, so you've got some sheet of charge, just some parallelogram there. Here, we got charge all over it. If you hear anything, that's raining on the tin roof of my barn. And what we're going to do, use Gauss's law. Got more right now. I shouldn't have said anything. We're going to draw they call it a Gaussian pillbox. The book does a rectangle because that matches the symmetry. If it's infinite, do you care? Do you know if it's rectangular or circular around the edges? You don't know. So I'm just going to draw the, the pillbox. We'll just draw a circle here, going down in, and it comes out at the bottom. This is your Gaussian surface. And since you say, well, we're doing a Gaussian surface to match the symmetry of the material, I probably should draw a little squares and squares there, or parallelograms. It's infinite, it doesn't matter. And a lot of books, except for this one, use pillboxes or basically cylinders for this. If you think of a pillbox, you know, the German pillboxes were kind of circular, so yeah, you know, they along the coast of France and stuff when we invaded Normandy. All right, and on D-Day, so we took them out of their pillboxes there. Now, so that's what we want to find. All right, so how do we do that? Well, Gauss's law, integral around a closed surface, E dot dA equals Q enclosed over epsilon naught. And so let's look at what we have. Well, the electric field, we know the electric field, it's going to have to be straight up here and straight down there. That's the electric field everywhere. So this is E dot dA. So what I'll say is for a pillbox here, if you do a rectangular type solid, you have to include all the four faces around. Here, we're just going to say that the cylindrical face, because we know the area unit normal vector is that way, and E is that way, E is up or down, they're perpendicular. And if they're perpendicular, E dot dA is 0. So what we want to do here, let's look at, say, the top and the bottom. Because the area unit normal vector at the top is that direction. At the bottom is that direction. So what I can say, I think pretty easily is, now we got to find Q enclosed. What's the Q enclosed? Well, we know if this is sigma. We know that sigma is equal to all the charge over all the area. Right? That was charge over area. And so the Q enclosed, sigma times that little, this would be that was over the whole area, so the charge enclosed will just be the sigma over the area enclosed. Because this is the ratio. That's the total charge over total area. I'll put total here. Well, if that's totals, it also works for whatever size of area we're looking at. As long as we have the ratio. We've got to keep the total areas the same on both. Okay. So that gives us Q enclosed. So we can come over here. See that Q enclosed on the top surface is sigma A. On the bottom surface, hey, okay, that just gives us 2 sigma area enclosed. Okay, E dot dA, well, I know E here is up, and the unit normal vector is up. The area there is just that total area enclosed. So at the top, it's just going to be E, area enclosed. And since this is sum, remember an integral is just a sum, so we're just summing up integrals of the area enclosed here, area enclosed there, and that one for doing E dot dA. So plus E area enclosed for the bottom. And if we do this, what do we have? This becomes 2E area enclosed total. And my apologies, I forgot something. One, I forgot the epsilon naught. This is over epsilon naught. And I did this actually for top and bottom. On this side, That's irrelevant. I made a mistake. Call it the barn dust, because, geez, it's everywhere out here. You can look around, see if you can see. You don't even see the floor there. I didn't sweep the floor before I did this. So, I shouldn't have done this. I should have just said, it's the area enclosed right here, and all the charge inside. So I really should just have put this. And that is my bad. That is my bad. Blame it on the barn dust, right? No. So the area enclosed cancels. I just get the electric field then is sigma over 2 epsilon naught. And what direction is it to make an electric field? Well, it's going to be up. It's going to be out, or normal to that surface. It's going to be normal to the surface. And that's the electric field using Gauss's law for an infinite plane. Not too bad. I like what it says in the book. I'm reading from the book. It seems surprising at first that the field of the infinite plane is independent about how far away you are. If you think about it, there's no distance dependency there. There's no distance dependency. What about 1 over r squared? Well, why is that? Well, I'll put why no distance dependency for E of an infinite plane of charge. Well, let's think of it like this, because there should be, you would think logically. If I'm just right above that plane, if I'm just barely up above, how much charge is affecting me? It's the charge right underneath me there, right? Because charge way out over there and way over there, like up the hill and over the road and everything like that. Is that charge going to affect me? It's so far away it doesn't affect me any. Really just a charge local to me affects the electric field. And it's really, if you think about it from individual points of charge, that's what's pushing me or pulling me down to it. Pushing me away or pulling me down depending on my charge. As I go way up there, I Superman up to 1,000 feet. Surveying the land around me. At that point, do I see more of that plane? Is stuff 50 yards up the hill there? That charge, it can see me. You know, a couple hundred yards, it can see me. That way, a few hundred yards. I'm affected by more charge since I'm further up. Since I'm affected by more charge, actually, it compensates. So as far as I go up, the electric field, say for the ones directly underneath me, they have less effect, but I get more charge affecting me. And since more charge is affecting me, it actually, they just compensate directly up. So as I move up, more and more charge affect me, the electric field stays constant up from a plane of charge. Now, it's infinite. That means it goes out to infinity. Well, what if I go up 1,000,000 miles away, Dr. Knight? Well, if it's an infinite plane of charge, it wouldn't matter, because the charge would keep on going. Now, of course, it's not reality, it's just a mathematical construct. But in that case, it would start mattering once you start seeing the edges. But for lots of things, if you're close enough to it, you never see the edges, so this is valid. Okay. They do next one in the book for a couple planes of charge. This is effectively a capacitor. And what they basically just say for a capacitor, outside the capacitor, because the two plates, the charge on one and the charge on the other one, their electric fields outside the plates cancels. And inside, they add up actually. And since they add up, because in a capacitor, one's positive and one is negative. Now in that case, they add up. And when they add, if they're both positive, you know, electric fields would this way, so they would cancel to be 0 inside. If one's positive and one's negative, electric field here is out. Electric field on the back side of the other one is in, so these actually add up. So the electric field for a capacitor is 2 of these. And what's 2 times this? Sigma over 2 epsilon naught n hat. Well, those cancel. So the electric field for a capacitor, which is just a charged plate, this one's positive and this one's negative, inside here, the electric field for a capacitor is sigma over epsilon naught n hat. And E equals 0 everywhere outside. Now, you guys are smart. What if we're real close right here? What if we're near this? Well, then there are what's called fringing fields. Actually, it does this, and it kind of, you know, and you get fringing fields on the outside. Can you calculate the electric field of these fringing fields? Yes. We didn't do that till grad school, so we don't want to do that here. Use transformation techniques tend to be the easiest way to calculate it. And so you basically take the equations you have, like, oh, I can't integrate, transform it to a different set of equations into their space, and then that space, you transfer it, you get the answer, inverse transform it back, and that gives you the fringing fields. That's how you do that. So electric field for an infinite plate and parallel plate capacitor. Now, the next, since they did the dot product of E, come over here, move my acetone to the other side, power supply, and move, since it's a barn, yep, got that here on the table. Yep, the old grinder. Now, let's look at the curl of E. 2.24 curl of E, of the electric field. Now, let's just think of the simplest things, a point charge. For a point charge, of course, the electric field, 1 over 4 pi epsilon naught, and we're going to say that's Q over R squared R hat, and there we go. And they want to know, what's the curl of it? Well, that would be del cross E, and you integrate that. Now, and we'd integrate that over, pretty sure that's over an area, but I just want to absolutely make sure before I tell you. Yeah, you integrate that over an area. dA over some surface. Oh, that's going to be a pain. Del operator, partials, and all that stuff. We could use fundamental theorem of curls, and we can say, well, this is equal to the integral of the electric field dot dl from around some perimeter, remember. Around some perimeter. And that's going to be what we want to do. But that we can do a little bit easier here. So what we want to do, we're going to set up, here's your coordinate system. We're going to say this is X, that's Y, and that's Z, which is zeta. And what we're going to do, we're going to start at some point A right here, go to some point B, and it doesn't matter the path, because we're only going to look at the endpoints of it. In the book, when they set this up, they call this R sub B, and this R sub A, and they say the path is like this. And you know from a path integral, if it's independent of path, what I could do is just look at it at the endpoints and do that integral and subtract it and work its way out. And that's what we're going to do. So let's do E dot dl. So if we do E dot dl, and then we'll do our integral. Or if we do E dot dl, now the book says to use spherical coordinates. Okay. And if you use spherical coordinates, what you're going to have is that E dot dl and this is because we're using just radiuses. It makes it easier. We don't want to integrate over x and y and z. Now you could. Spencer Whalen may want to do that integration. So can anybody else mathematically. Angel, probably not. And I don't blame her. Let's do it over one coordinate, just a radius, and just have that arcs around. And we just do it over that. It gets easier. So that's just going to be equal to 1 over 4 pi epsilon naught q over r squared dr. And we're dotting it, so when you dot it, r hat E dot dl, the r hat for E dotted with dr vector is just going to give us dr. That's why I can just put dr there. Hopefully it's not too small that you can't see it. I'm just saying the dot product, the vector nature, this is from E direction, and this is the differential vector where we're doing it over our perimeter, and then it just gets dr there. Okay. Now if we do that, what are we going to get? Well, you know, it's basically just when we integrate this, we're going to do this from r sub a, r sub b. It's just going to be equal to 1 over 4 pi epsilon naught q over r squared, r sub a, r sub b, dr. Well, that's just going to be 1 over r squared because the q is constant. So the integral of 1 over r squared is just negative 1 over r. Polynomial integration, we should know that. R to the negative 2, add 1, move it underneath, so it's negative 1, so that goes out front. And plus negative 2 plus 1 is negative 1, so it's 1 over r, 1 over r equals r to the negative 1. You didn't like my yoga voice, I guess, did you? Or my, that's when I do my chanting, my chakras. Whatever, I don't know, I'm just making stuff up. This is my 4th video. I've been doing 211 beforehand, so I'm getting a little goofy. I haven't had any of my seltzer water lately, so maybe I'm getting a little lack of liquid in the brain. So if I do that, I end up with the 1 over r, so this is going to be equal to negative 1 over, we'll say q over 4 pi epsilon naught. And that's just going to be 1 over r evaluated from r sub a to r sub b. Well, when you do that, you get q over 4 pi epsilon naught. Negative still is going to be out front. 1 over r sub b minus 1 over r sub a. I could run the negative through and switch those around. Doesn't matter, actually. It doesn't matter. Now we won't do this integral around a closed path. So if it's a closed path, you know, it's going to go back to where it came. If it's a closed path, because r sub b becomes r sub a, the vector anyway, and so that's 0. So the curl of E equals 0. So what we can say here, does the so del cross E for a point charge is 0. And I dropped my cap. Okay. Now, I like what it says in the book. This is after all perfect arbitrary. No matter where the charge is located, this is held. If we have many charges, it works. You just add them all up because of superposition. So bottom line is del cross E is 0 for any static charge distribution. Charge isn't moving. Charge is not moving. Because one charge, any charge distribution is just a sum of many charges, and we just sum up the effects. What's 0 plus 0 plus 0 plus 0 plus 0? with 0, of course. Okay? And that is the finish up here on electric field. We'll stop the video, erase it, and we're going to talk about then electric potentials.